Alright, it's been a bit since I've done a video, but I figured I'd go back and work on some more Spivak exercises. Okay, so full disclosure, I really don't like this exercise. Because the main things are we have these words here, integrable and continuous, that we use throughout this exercise, and we don't know what these are yet. Although, this textbook is meant to be taken probably after you've taken Calc 1 and possibly Calc 2. So you should be familiar with like what an integral is and what a continuous function is. But the definitions that you learn when you learn them for the first time, you don't really learn the definition. There are very specific, theoretically rigorous definitions, sort of like the ones that you'd see in a theoretical linear algebra course, which I think is more of an actual prerequisite for this book. I think there's some things from linear algebra that you need. So hopefully you've seen like proof-based, pure mathematical linear algebra. So, anyways, we don't know what integrable and continuous mean, so we can't really do this problem. But I'm going to try to do it anyways and sort of brush over some of the details, and I'll just ask you to trust me on a few things, like a few facts about integrability and continuity that we haven't proved yet. And let's see here. I know the integrability. Yeah, these are things that will be proved later, but they're not proved here. So, anyways, so first for A, so I should probably say that we're doing A. So recall that the Riemann integral, and you can write the integral from a to b of f, or you can write the integral from a to b of f of x dx. However you want to write it. Is defined as the limit as n goes to infinity and min xi plus 1 minus xi goes to 0 of the sum from I equals 1 to n minus 1 of f of ti times xi plus 1 minus xi, where x1 is precisely a, and that's strictly less than x2, which is less than, we keep going and we all get all the way to xn, and this is b, and each ti is chosen to belong to the interval xi to xi plus 1. Okay, so basically what's happening here is you break the interval from a to b up into a whole bunch of intervals. X1, the interval from x1 to x2, then the interval from x2 to x3, etc., until you've got a partition of the entire domain. And then for each of those partitions, you choose a point in that interval, for each interval in this partition, you choose a point in that interval, evaluate the function at that point, and multiply by the length of the interval. And so what this looks like on a graph is you just take, it's sort of like if you look at graphs that describe the Riemann integral, let's say you break your domain up into like 4, so this is A and this is B, you break it up into, let's say n is equal to 1, 2, 3, 4, right? No. 1, 2, 3, 4, 5. N would equal 5 here. So this is going to be x1, x2, x3, x4, and this is x5. And then, so we've got 4 intervals here. And for each one, we choose some point. It doesn't really matter which point. And then you go up to here. You see where it, so this is x, this is y. and this is y equals f of x. And you choose this point, and then you choose this point. You basically take the image of each of these points, and then you sort of make a box. And then what this sum does is the sum just finds the area of these boxes. So you take the area of every single particular box, because the height is f of, because this will be t1, this will be t2, etc. So the height of this box is f of t1, and the length of the box is x2 minus x1. And so you just add those up, and so this is going to be an approximation of the integral. Because you see, if you're to calculate the area under the, if you were to find the area of these rectangles, you can visually see that it would be close to the area under this curve. So that's how we interpret the sum. Sometimes this xi plus 1 minus xi is written as delta xi. It doesn't matter. But if you take the limit, the idea is that if you take such a partition where you go from x1 to xn, if you make finer and finer partitions, meaning that n gets bigger and bigger, and you make sure that you're sort of breaking up basically each of the intervals needs to get small, which is why we have the minimum of xi plus 1 minus xi goes to 0, meaning, oh no, this should be the max. So the reason that we do this is that this ensures that as we take a finer and finer partition of the interval from a to b, the intervals themselves get smaller and smaller. And it turns out that if you take this limit and choose the ti's however you want, it doesn't matter how you choose them. If this function is integrable, then you'll arrive at the same thing. And so we say that a function is integrable if this limit exists. And so, as you can see, there's a lot of stuff you have to do there, and there's a lot of things that you would have to do to prove that this actually works out the way that I'm saying that it works out. But it does. So we need to use this. Alright. So having done this, we want to prove this inequality here, and it says to do it this particular way looking at the integral from a to b of f minus lambda g squared. We're not going to do that, because I don't really understand how you would do that or why it would be useful. My impression is that it's going to look something like the proof of theorem 1-1, 2, which will actually end up, it's mentioned later on in the exercise here, and we actually end up using it as well. So anyways, with this setup, what we're going to do let x and y be vectors. So these aren't real numbers anymore. These are vectors. Defined by, so x is going to be x1 through xn. No, it's going to be x1. So here, x equals x1 through xn minus 1. So Spivak likes to put indices of a vector as an exponent. I really don't like that because that makes it confusing when you're dealing with actual exponents. So I instead use them as subscripts like I've written here, which is pretty normal. I haven't really seen many people do it the way that Spivak does, and I don't know why he does it that way. It's confusing. I don't like it. But anyways, so this is x, and how do we define each xi? So xi is going to be defined as we take f of ti times the square root of xi plus 1 minus xi. Wait. we do need n. Because xi plus 1, so x, no, what am I doing here? I should not use x and y as my letters. So these are vectors, we're going to make them u and v. So u and v are going to be vectors, and u is going to be u1 through un minus 1, and ui is going to be f of ti times the square root of xi plus 1 minus xi. Right, so we need to go up to un minus 1 because then we'll get up to xn. Right. Because we have n minus 1 intervals in this partition. So this is, so given any function f and a function g and a partition x1 through xn, and also we've got ti's where each ti is in the interval from xi to xi plus 1. And v is defined similar. V is v1 through vn minus 1, where vi is g of ti times the square root of xi plus 1 minus xi. Then, let's look at the absolute value of the sum from I equals 1 to n minus 1 of f of ti times g of ti times xi plus 1 minus xi. So this is, just by definition, the sum from I equals 1 to n minus 1. Well, f of t, so what we can do is we can break this xi plus 1 minus xi, we can break that up into square root of xi plus 1 minus xi times square root of xi plus 1 minus xi. And if we take one of those square roots and combine it with f of ti, then we end up with ui. And if we take the other square root and combine it with g of ti, we get vi. So we have the sum from I equals 1 to n minus 1 of ui vi. And we know by theorem 1-1, 2 that this is less than or equal to the norm of u times the norm of v. And what is the norm of u? It's the square root of the sum from I equals 1 to n minus 1 of, we take each of the ui's and square them. So we take f of ti and we square it, we get f squared of ti. And we square the square root of xi plus 1 minus xi, and we get xi plus 1 minus xi. And again, it's the square root of this entire thing. And then the sum from I equals 1 to n minus 1 of g squared of ti, xi plus 1 minus xi, square root of this entire thing. Okay. So now, if we take n to infinity, and the max of xi plus 1 minus xi to 0, so if we consider finer and finer partitions, then what's going to happen? The left-hand, so we have this inequality here. So the very left-hand side of this inequality, when we take the limit, well, look, this sum, when we take the limit, is just by definition the integral of f times g. So on the left-hand side, we have the integral from a to b of f times g. And so that also uses the fact that we're taking a limit, and you take a limit of an absolute value, and it turns out that the limit of an absolute value equals the absolute value of a limit, and that's because the absolute value function is continuous, which again is something that we need to use here, but which we haven't talked about rigorously. And so again, we're using things that we haven't learned yet, but that's the only way to do this problem. This is less than or equal to Now, this thing, if we look at the very right-hand side of the inequality above, this sum of f squared thing, this whole thing inside the square root, when we take the limit, we end up with the integral of f squared. And you can take the limit inside that square root because the square root function is continuous on the positive real numbers, again, using things that we haven't learned. F squared. So we end up with this, and then we get the same thing for g. And look, that's the exact inequality that we wanted to prove. And so we're done. Now, it's possible, so I keep saying that like we have to use things that we haven't learned yet to do this one. Maybe if we did it the way that they wanted to do it, you could avoid some of it. But the fact that we had, there's no way you could possibly prove something about integrals without having rigorously proven the definition of an integral, which we haven't done, so you can't do it. So there's no good way to do this problem, but here's one way to do it. Anyways, moving on to B, what do we have? So basically what we need to prove is that so if equality does hold in this inequality that we've just proven, does that mean that f equals lambda g for some lambda? In general, equality in A does not imply that f equals lambda g for some lambda, and this is because we can change the value of f at one point without changing the value of the integral from a to b of f. And this is true in general. And this is, again, another thing. So this is an even deeper, more significant fact about integrals. That if you take a function and then you consider, if you take an integrable function and you consider the same function, but you change the value of the function at one point, then taking the integral doesn't change at all. And this is an important fact about integrals. I think it's usually talked about a little bit when discussing Riemann integrals, at least when you talk about Riemann integrals theoretically and rigorously. But you don't really talk about it where it's more natural and comes up more naturally is when you start talking about the Lebesgue integral, because what happens is a singleton point is a set of measure 0, and changing the value of a function on a set of measures, changing the value of an integrable function on a set of measure 0 does not affect the value of the integral. And that's a very, that you need to do some work to prove it, and we haven't done that work, so we aren't allowed to say it, but we have to say it here because that otherwise we can't. You need to know this fact in order to answer this exercise. So you need to know that changing the value of a function at a point doesn't change the integral in order to say that equality in A does not imply that f must be equal to lambda g. Okay, but suppose f and g are in fact continuous. And there is no lambda in R such that f equals lambda g. Equivalently, for every single lambda in R, so if it is the case that there is no lambda such that f equals lambda g for, so if there does not exist a lambda in R such that f of x equals lambda times g of x for all x, then for every single lambda, there must be some point such that f of x is not equal to lambda of g of x. So, if f of x is not equal to lambda of lambda times g of x, then f of x minus lambda times g of x is not equal to 0. And then if we square both sides, we get f of x minus lambda g of x squared is not equal to 0. However, we're squaring something. And whenever you square a number, it's either, if you, any real number squared is going to be greater than or equal to 0. So we're saying that this quantity squared is not equal to 0, which means that it must be greater than 0, because it's some number greater than or equal to 0, which is not 0, which is precisely what it means to be greater than 0. Okay, next page. By continuity, and of course, now we have to use a fact about continuity, which we don't know yet because we haven't learned the rigorous definition of continuity. F minus lambda g squared is greater than 0 in an open neighborhood of x. And what is an open neighborhood? We don't know yet because we haven't learned the definition again. So again, we're using things that we don't know because that's what we need to do in this exercise. So that is, there are numbers A, B, C, D, C and D such that x is in the open interval from C to D. And f of y minus lambda times g of y squared is greater than 0 for all y in C to D. And why are we able to do this? We're able to do this because of continuity. How do we know that continuity gives us this? Because you use the definition of continuity. What is the definition of continuity? We don't know because Spivak hasn't told us, so just trust me on this. Okay, so thus, if we take the integral from a to b of f minus lambda g squared, then this has to be greater than 0 because there is a neighborhood around, so there is an open interval from C to D which contains x, and on this interval this function is strictly positive. And if you take a function which is strictly positive and integrate it over an open interval, you end up with a value which is greater than 0. Okay, so we know that on the interval from C to D, if we restrict this integral to C to D, then integrating the function will give us something positive. But then if you consider the integral of the remainder of the region, well, it's the function is always greater than or equal to 0, so it will never be negative, so you can't cancel out with the positive integral that you've obtained over this region from C to D. So we can guarantee that this integral is positive. And then if we FOIL this out, we just FOIL out the thing that we're squaring and then break up the integral because an integral of a sum is the sum of the integrals. So it becomes the integral from a to b of f squared minus 2 lambda integral from a to b of f times g plus lambda squared, which is the integral from a to b of g squared, is greater than 0. Okay? So now what? Now note that at the beginning, what we said, suppose f and g are continuous and there does not exist. So equivalently, for all lambda, blah, blah, blah. Okay, so when I say equivalently for all lambda in R, there exists an X such that this holds. So, given any such lambda and X, we get this inequality, and so everything follows. So if you given any such lambda and X which satisfies this thing, so if you choose any lambda, you find the X such that f of X is not equal to lambda times g of X, and then you do the rest of this argument, and then you prove that this thing that we have at the end here with the three integrals is greater than 0. And the important thing is that this holds for all lambda in R. Because for every particular lambda that we're given, we prove this inequality. Therefore, this inequality holds for every single lambda in R. Thus, we have a quadratic. How do you spell quadratic? I think it's a T. Quadratic in the variable lambda with no real roots. Because look at this. First of all, this is indeed a quadratic in lambda because we have a constant term. So we have this term with a lambda, and we have this term with a lambda squared. So we have a lambda squared term, a lambda term, and a constant term. That's a quadratic. And by the way, this whole thing that we're doing right now, this should look familiar if you read through the proofs in the textbook, because this is very similar to the proof of 1-1, 2, which is in fact the thing that we used in part A of this exercise. Anyways, thus we have a quadratic in lambda with no real roots. This means it must have a negative discriminant. Because a real quadratic with no roots, because if a quadratic has a discriminant which is greater than or equal to 0, then it has real roots. And it doesn't have real roots, meaning that its discriminant must be negative. i.e., 0, so it's 0 is greater than the discriminant. Okay, so what is the discriminant? Or here, let's start with the discriminant itself. So it's, let's see here, b squared minus 4ac. So b squared is the coefficient of the lambda term squared. So the coefficient of the lambda term is minus 2 integral from a to b of f of g. So if we square that, the negative 2 squared becomes 4, and the integral from a to b of f of g squared, well, that's just integral from a to b of f of g squared. So it's b squared minus 4ac. So now we subtract 4 times a, which is the coefficient of the lambda squared terms, which here the coefficient is integral from a to b of g squared, integral from a to b of g squared, times c, which is the constant term, which is the integral from a to b of f squared. So this is the discriminant, and this is negative. Okay, and now what? So what we can do now is we take this minus 4 term and move it to the other side, and then we cancel out the 4's, and then we take the square roots of each side, and then we'll end up with the square root. On the left side, we'll have the square root of integral from a to b of f times g quantity squared. So the square root and the square will cancel out, and so we're just left with the integral from a to b of f times g. And this is less than, so here on the right-hand side, we'll have positive for integral ab g squared, integral of f squared. So the 4 will cancel because we've canceled that. And then we take the square root of everything, and so we'll have the square root of the first thing, which is integral from a to b of f squared. We'll have the square root of this, and then the square root of the other thing. Okay. So, if there is no lambda such that f equals lambda g, then the integral of fg is strictly less than this thing. So this is the inequality that we have in part A, but with strict inequality. So we've proven that if there is no lambda in R such that f equals lambda g, then we have strict inequality in A. Contrapositively, meaning that we take the, so if A if you have two statements A and B, if A implies B, the contrapositive states that not B implies not A. And so we can basically do not the conclusion here implies not the assumption. So the conclusion here was strict inequality in part A. And so if we take the negative of that, that means it is not the case that we have inequality in the inequality from A. So if we don't have strict inequality, then we must have equality. So the contrapositive says that if it is the case that we have equality in part A, then it is not the case that there is no lambda in R such that f equals lambda g. So if it's not the case that there is no lambda in R such that f equals lambda g, well, that means that there is a lambda in R such that f equals lambda g. So the contrapositive of the statement says that equality in A implies there is a lambda in G such that f equals lambda g. So contrapositively, by the way, I hope that wasn't super I don't know, it can be tough to gauge the level of my audience because I forget what sorts of things I was comfortable with and what sorts of things I wasn't comfortable with when I was at the point where I was doing this type of thing. But doing contrapositives is a very important part of writing proofs in mathematics. It's a very useful tool. And so, yeah, if you've done a lot of proofs, then you're probably very familiar with it. And if you're still getting used to proofs, then it might be unfamiliar. So I hope I wasn't, like, talking down or anything. I didn't intend that. But anyway, so contrapositively, if equality holds in A, then there exists a lambda such that f equals lambda g. And again, this is only in the case of f and g being continuous, because you need to have continuity in order to prove that there are numbers c and d such that f minus lambda g is positive on the interval from c to d. And so again, if you don't have continuity, then you can just change the value at a point, and it doesn't matter. Which, again, if you're changing something at a point, you're not changing something in a neighborhood. Okay, so now the last thing, part C, meaning show that 1-1, 2 is a special case of part A of this exercise. So, given x and y, given vectors x and y, let f be the sum from I equals 1 to n of xi times the indicator function from I minus 1 to I. And similarly, g equals sum from I equals 1 to n of yi, indicator function I minus 1 to I. Now, I personally did not see the indicator function until I took measure theory. So basically, the indicator function of a set is 1 on that set and 0 elsewhere. So if we take the indicator function of the interval from 0 to 1, that function will be 1 at any point between 0 and 1, and it will be 0 anywhere else. So if you take the indicator function on 0 to 1 and evaluate it at 1/2, it will be 1. If you evaluate it at -1, it will be 0. If you evaluate it at 2, it will be 0, and so on and so forth. Okay, so what this function f does is, on the interval from 0 to 1, it will take the value x1. On the interval from 1 to 2, it will take the value x2, etc. Then, the sum from I equals 1 to n of xi yi is going to be equal to the integral from a to b of f times g. And this, I suppose, is not an entirely obvious fact, but if you think about it, the way that you define the Riemann integral is you just take, you partition the domain you partition the domain, and then for each interval in this partition, you make a rectangle, and then you add up all of the areas of these rectangles. And so it makes sense that if you've got a function which is already a whole bunch of rectangles, because again, that's how we defined f here, it's just a bunch of rectangles, then eventually when you take the limit, you'll get the just the area. So I guess this is an easier fact to understand if you've taken measure theory, which you are not expected to have done if you're learning this for the first time. But given that there's enough stuff in this problem that you need outside knowledge in order to prove, I'm not too worried about this. But anyways, by part A, this is less than or equal to integral from a to b of f squared times integral from a to b of g squared. No. I know this is a long video. Please, I'm almost done. Just hang in here. And this is precisely the norm of x times the norm of y. Okay, and now we're done. So I'm going to talk a little bit more, but I finished the proof, so you don't need to stick around if you've gotten everything you need. The important thing that I want to note here is that this is really, really bad, because what have we done? We've proved part A of this exercise using 1-1-2, and now what we're doing is we're proving 1-1-2 using part A. And so it's cyclic reasoning. So this is not a valid proof of 1-1A, because we've used 1-1A as part of this proof. So what I really think we're intended to do is, so like we showed before, or like I mentioned before, the textbook has another way of doing part A that it recommends. And I'm guessing that method of doing part A does not involve using 1-1A. I assume there's other techniques that you use in that. And if you're able to use other techniques in that, then you are able to conclude 1-1-2 from part C, because if you're able to prove part A without using 1-1-2, then this proof is entirely independent of 1-1A. Just looking at the way that it's stated, I think that what you end up doing is, so we have this argument here where you look at f minus lambda g squared, and then you FOIL it, and then you use a discriminant argument. I'm guessing that that's sort of a similar thing that you do if you want to prove part A the way that they suggested. And furthermore, that's actually similar to the, and I mentioned this before, that's similar to the way that it's proven. That's similar to the way that 1-1-2 is proven in the textbook. So my guess here is that the real key of this fact, of 1-1A, the real core element is the argument used in 1-1-2, that discriminant argument. I think that's the real key. That's what you really want to be using, because my guess is that it's basically this 1-1, or this part A of this exercise becomes a true generalization of 1-1A, because I'm guessing you end up using a similar technique, but proving a stronger statement, because the statement that you prove implies 1-1-2. And that's an important idea in mathematics, is taking a proof and using the same idea of the proof, but generalizing it to a more general situation, and thus being able to prove stronger results. So anytime you can take a proof and generalize it and get a strong result, that's good, because you've sort of gained more knowledge using the same techniques, and so you're really using those techniques to the fullest potential. But yeah, so I just wanted to mention that. I think there's a better way to do part A of this, and if so, then this is not cyclic. But the way that this is given here, it's cyclic, so given the proof of part A that I've shown, you cannot deduce 1-1-2 from part C, because C relies on A, and A relies on 1-1-2. And, alright, that's about it. We are now done with this exercise.